Biology students, this is the third video of the class, and we're continuing on with chapter number 1, and this is where we left off at this particular point. Let me see if I can get this up here for you. Okay, there. So what is a theory? What is a scientific theory? In order to understand what a scientific hypothesis is, and a scientific theory is, and what a scientific law is, we have to put it in context with regards to how scientists think. And to make a long story short, scientists use something called the scientific method to study problems of interest to mankind. And that includes anything that you might think of. Gravity, electromagnetism, radioactive decay. And so when we're interested in something in science, we come up with a hypothesis. A hypothesis. What is a hypothesis? Well, you probably learned in high school that somebody might have told you that a hypothesis is an educated guess. And that's really what it is. It's an educated guess with regards to some problem that is of interest to scientists. For example, the Neanderthals, an ancient form of humans, died out about 30 to 40,000 years ago. What type of hypotheses, that's the plural of hypothesis, could you come up with to explain the fact that we're here and the Neanderthals are no longer here? What happened 30 to 50,000 years ago to wipe out or cause the extinction of the Neanderthals? In your own mind, think of some things that make an educated guess as to what may have been the cause. Well, I can think of a variety just off the top of my head. Maybe our ancestors killed them off. That would explain the fact that we're here and they're not. Maybe it was disease that wiped the Neanderthals out. Maybe when our ancestors, to put it in context, the Neanderthals were a type of human that left Africa and conquered Europe and Asia before our ancestors, Homo sapiens. And then only later on did our ancestors, Homo sapiens, and the ancient form of Homo sapiens is called Cro-Magnon man. Only then did Cro-Magnon man leave Africa through the Middle East and come into contact with these Neanderthals. We see that wherever our ancestors encounter the Neanderthals, after a few generations, the Neanderthals are gone. That would indicate that maybe we wiped them out, or maybe we outcompeted them in some other way. Maybe we spread some sort of disease to them, like Columbus spread diseases to the Native Americans and wiped them out. But the hypothesis has to have some logic to it. It has to fit what we see. So we see that the Neanderthals left Africa prior to us, and they settled Europe and Asia. We see that Homo sapiens, Cro-Magnon man, left much later, and after a few generations, the Neanderthals are gone. So let's come up with a hypothesis. Let's say that our ancestors killed off the Neanderthals. would you test that hypothesis? And that's the important thing, ladies and gentlemen, is a hypothesis must be testable. If you cannot test the hypothesis, that's not science. That's just speculation. There's all sorts of things we can, as human beings, we can be curious about and speculate about. But if we're going to use the scientific method, we have to have a testable hypothesis. So let's say that our hypothesis is Cro-Magnon man wiped out in battle the Neanderthals. How would you test it? Well, it makes sense that we go out in the field and we look at these old places in Europe and Asia where the Cro-Magnon man met Neanderthals. We could look for evidence that the Neanderthals had broken bones or spear points in their body, and we could look for evidence of battle, of broken bones, and injuries to the skull from weapons. Those would support our hypothesis, wouldn't they? So once you have your hypothesis, you test it. After you test your hypothesis, you can do one of two things. You can either reject the hypothesis, throw it in the garbage, it doesn't make any sense, or you can fail to reject. It's very important that you keep in the back of your head, you can never accept a hypothesis. The best you can do is fail to reject. So let's say we do find lots of evidence that there were battles and the Neanderthals lost these battles. The evidence would be, as I mentioned, damage to the bones and weapons around the sites where the clashes occurred, and the disappearance of the Neanderthals and the development of Cro-Magnon communities in those areas formerly inhabited by Neanderthals. Then what we do in science is we test that hypothesis over and over and over again. And if we still fail to reject, then we can say, it's still not a fact, but we can say, well, it looks like this is the best explanation. And then you and your co-researchers would write a paper on it. And the paper is published in digital format and in paper, and so that scientists all around the world can see the method in which you test your hypothesis and your conclusions, and they'll evaluate you, and that's called peer review. P-E-E-R review. Peer review is done to keep scientists honest, and so people will try and look at your data and see if it makes sense, and see if your conclusions make sense. And if they don't, they're going to tear you apart. There's no way. That's the beauty of the scientific method. It forces people to be honest. If you run a laboratory experiment and to test your hypothesis, for example, other people are going to run that same experiment. If they don't get the same results, they're going to say you falsified your data to support your hypothesis, and your scientific name will be ruined, and you will no longer be taken seriously. So peer review is a very powerful method, and you're going to have scientists from all the best universities in the world: Harvard, Cambridge, Stanford, University of Tokyo, University of Berlin, Cambridge, Oxford, Adelaide, Beijing, Johannesburg, and they're all going to read your paper. Sometimes it'll be translated in other languages so that those people can study your results. Then, if that hypothesis is tested over and over and over again for decades in hundreds of studies you still can't reject that hypothesis, then it can become a scientific theory. So, ladies and gentlemen, a scientific theory is a much more powerful thing than a hypothesis. It has stood the test of time. A scientific theory is something that other scientists are going to use to study things related to that theory. Good examples of scientific theories include that geologists used are the theory of biological evolution and the theory of plate tectonics. We've tested them for hundreds of studies, thousands of studies, and we cannot reject those scientific theories. They're powerful. They work. Biological evolution. It's been tested for more than a century, and it still works. It helps us develop vaccines, helps us develop new medicines, antibiotics, insecticides. It helps us in so many different ways. It's the foundation of modern biology. So, there are other theories in other sciences that I haven't mentioned, like the theory of gravity, or a theory of electromagnetism. But these are powerful things. Now, if a scientific theory has been tested for an enormous amount of time, maybe a century, and we have never been able to reject that hypothesis, it could become something even more solid called a scientific law, like the law of gravity. We have not seen any place on planet Earth Houdini or anybody else can't defy the Earth's gravity. It holds us to the Earth. It holds the planets around the sun. It holds the moon around the Earth. And it holds the star systems the stars in our galaxy around the dark hole, the black hole in the center of the Milky Way galaxy. So a scientific law is the most powerful thing we have. Knowing that, we still have to remember the emperor has no clothes. I'm sure you've heard that. You still have to have an open mind, so that if some data comes out one day and it suggests that our scientific theories or laws are to be rejected, we have to go with it. One must keep an open mind. A good scientist will keep an open mind. For example, if you're studying something, be it global warming, whatever, and you don't go in there as a Democrat or a Republican trying to prove a point. A good scientist, it will go in there and say, this data doesn't fit my political and personal point of view, but I have to go with it because I want to be a good scientist. I want the truth. That's a good scientist. Let's talk a little bit about our universe. And once again, I mentioned the fact that the Earth is 4.6 billion years old, and we think that the universe is 13.7 billion years old. The universe formed in a Big Bang 13.7 billion years ago. We'll talk about why we know that later on in great detail. But for the moment, I'll just say the very basics. There was a man named Edwin Hubble in the 1920s, a great American scientist, and he looked out at the stars in the night sky, and he noticed that the stars are moving away from our star, right? And also the galaxies are moving away from our galaxy. Think about it. If the universe is expanding, which it is, then it must have been smaller in the past. Smaller in the past. smaller in the past. Until 13.7 billion years ago, our entire universe, all of the matter and energy in our universe, was concentrated in a point so small you could fit it on the head of a pin. So, the astronomical evidence clearly shows that a great explosion occurred 13.7 billion years ago, creating all of the matter and energy in our universe. And the universe continues to expand. We're going to talk about that more. I just touched on the on the detail, on the basics of it in a later chapter. If you are having difficulty in understanding how the universe is expanding and how that has to do what that has to do with the Big Bang, think about raisin bread. Take a look at the left-hand side and notice that you've got these 6 raisins in your slice of bread. Let's say you put the dough in the oven and the bread becomes larger. The raisins are then farther apart, right? Same thing with our universe. This central raisin might represent, for example, our Milky Way galaxy. And our Milky Way galaxy is a certain distance measured, depicted by these black lines, these line segments between other raisins. Notice after the bread expands, due to you toasting it, that the raisins move apart. Same thing with our universe. The stars were closer to our the universe. The galaxies were closer together, and now they're farther apart. Our universe is expanding. What that will lead to eventually, we'll talk about later on. So, we have a sun, and we have 8 planets. The planet that's closest to the sun is Mercury, followed by Venus, then Earth. Earth is the third rock from the sun. One of my daughter's favorite TV programs, the third rock from the sun. Fourth planet from the sun is Mars, which we're going to visit in the next 10-15 years. Then we got Jupiter, Saturn, Uranus, and Neptune. 8 planets you need to know about. Pluto, notice that its orbit is way off of the other ones. All the other ones are on a disk. And that disk is called the Ecliptic Plane. The Ecliptic Plane. So, the best way to imagine the Ecliptic Plane is, I'm from an older generation than you. I was born in the 1960s, and when I was your age, we didn't stream music or listen to it online. There was no online. So back in those days, how do you think I went to buy Led Zeppelin or Pink Floyd albums? Well, I had to go and ride my bicycle to the record store, and I'd buy the vinyl, 33 or 45 singles. Anyway, you know what they look like. You've seen them. If you imagine an LP, it's just like our ecliptic plane. All of the planets, the Earth, all of the moons, all of the asteroids, those are the rocks that the hundreds of rocks, large rocks that are between Mars and Jupiter and the sun, are all on the ecliptic plane. Pluto is out of kilter, isn't it? It was knocked out of kilter by an impact with a comet or probably a comet. And but it originally was on the ecliptic plane. We're not really too worried about Pluto because it's not one of the planets. It's kind of small. We're going to focus mainly on what we have in our solar system. And we're going to learn about how our solar system formed 4.6 billion years ago. The sun is enormous, huge, and obviously you know that what holds the planets in orbit is the gravitational pull of the sun. What holds moons in orbit around each of the planets is the gravitational pull of the planets. So we have one moon, and it's held in orbit by Earth's gravity. Back in the 1950s, there was, during the time of the Soviet Union, Premier Khrushchev wanted to get to into space before us. And who is us? Well, that was during the Cold War, and the world was divided into the communist world and the free world. And we wanted to get there before the Soviets. Premier Khrushchev, though, had sent out a satellite called Sputnik in the late 50s into outer space. And that was the first step in them developing rockets so that they could go to the moon. So President Eisenhower and President Kennedy set us on a path. Back in those days, Republicans and Democrats worked together instead of fighting, and we sent our spacecraft out to the moon. And in your grandparents' day, or maybe your great-grandparents' day, you can imagine them in the early 60s looking at their black and white televisions and watching those brave men go onto the moon. I'm sure you've heard their names: Armstrong, Neil Armstrong, Buzz Aldrin, etc. And so finally human beings had left the planet and gone onto the moon. After that, though, you might know it as well, but in the late 60s to the 80s, we explored all of the planets. The first planet to be explored was Mercury. Mercury is the closest planet to the sun. And it's also the smallest planet. This was visited by the Mariner missions. I think it was 1972, 1970, something like that. But it was the first planet visited. We quickly realized that life could not exist on Mercury. Why do you think that might be? Well, look how close Mercury is to the sun. You think it might be hot there? It's hot. It's so hot there that you can melt lead on Mercury. Second thing is Mercury is so small. If an object is small, it has less gravitational pull, right? So there's no atmosphere around Mercury because there's not enough gravitational pull to hold those life-giving gases, such as oxygen and also water. So Mercury is not a good candidate for life. Second planet from the sun we visited was Venus. Back in the 19th century, people would look out through their telescopes and they would imagine that there would be life on Venus. We could see lakes and rivers by looking at through our we could see clouds and storms, and many people called Venus our sister planet. However, we were deeply disappointed in the 70s when our unmanned spacecraft, went into the Venetian atmosphere and found that life could not possibly exist as we know it on Venus. Why? Well, it's closer to the sun, right? Also, its atmosphere is 95% carbon dioxide. Carbon dioxide is a greenhouse gas that holds heat in. We're worried about global warming on Earth because CO2 concentrations have reached 0.033%. Venus has a 95% carbon dioxide atmosphere, plus it's closer to the sun. Do you think Venus might be hot? Yes. Venus, temperatures on Venus are like an oven on broil. Also, those lakes and rivers are filled with sulfuric acid. The clouds are not water, they're also sulfuric acid. It would destroy any life. So we don't think there's life on Venus. We're going to spend the rest of the semester talking about planet Earth, so I'm not going to talk about that now. The 4.6 billion years of Earth history that we study in historical geology. But the next planet is quite interesting, Mars. And both the Democrats and Republicans want for us to get to Mars in the near future. Maybe 10 years, maybe 15 years. That's going to be exciting for your generation. It'll be just like your grandparents or your great grandparents watching those astronauts go to the moon. It's going to be 9 months to get there. 9 months. It's a long journey. And there could be life on Mars because there's water on Mars, both frozen and liquid. What's water? H2O. So you can use a chemical process called hydrolysis to change the water into oxygen and make a breathable atmosphere if you have a dome structure there. There will be colonies on Mars and the moon eventually. Geologists don't think in terms that most people think. We think in thousands and tens of thousands of years. There will be space travel to Mars and the moon, and we'll colonize it eventually and go beyond that. I think it's important that we get there before some other country gets there. That Democrats and Republicans actually work together to do this. The 4 inner planets, Venus, Mercury, Earth, and Mars, are similar. So, we have a name for the inner planets. They're called the terrestrial planets. Why do we? What do the 4 inner planets have in common? They're small, and they're close to the sun. Once we go beyond Mars, we get to this 4,000 or so rocks in the asteroid belt. Japanese spacecraft have already landed on the asteroid belt, and so have ours. And they're mostly made of ice and also rock. And we've dated them. They're 4.6 billion years old. Beyond the asteroid belt, we get to the largest planet in our solar system called Jupiter. Jupiter, our spacecraft visited Jupiter in the 80s, and we found that it's not a good candidate for life because it's so far from the sun that it's so cold there that the atmosphere is made of poisonous liquid hydrogen and helium. That red spot is a poisonous gas storm on the surface of Jupiter. Plus, look how big Jupiter is. The bigger something is, the more the gravitational pull is. If an astronaut were to land on Jupiter, let's say a big guy like Shaquille O'Neal, 6 foot or 7 foot something guy and 300 pounds, he'd be squashed to the size of a thimble by the gravity on Jupiter. So we don't think life could exist on Jupiter due to its high gravity and its low temperatures and poisonous gases. However, of the dozens of moons that revolve around Jupiter, there is the best possible place where we can find life outside of Earth in our solar system. And that's the moon Europa. This is what Europa looks like, ladies and gentlemen. It's covered by water, ice, and the ice in some places is just less than 100 feet thick. Underneath it is an ocean. Europa has the second ocean in our solar system. Our oceans are about 4 billion years old, and life appeared after just 500 million years old. 500 million years. The European Ocean is 4.6 billion years old. You tell me, will there be anything intelligent living underneath that ice? Look at these cracks in the ice. That means the ice is moving. It's not that thick. The other mission that NASA and other space agencies want to do is to send an unmanned spacecraft to Europa with a heating core to melt through the ice and to put in a submarine with video so we can video, and also with lights, headlights. It'll be like an SUV driving into the woods searching for life. That's going to be an exciting day when we send our spacecraft to Europa. I think we need to, as a nation, need to do this. We want to get there first, and also we develop lots of technologies that benefit our country and the world, such as satellites, microwave ovens, and the internet. Beyond Jupiter, we get to Saturn. Saturn is the second largest planet in our solar system. It's even farther from the sun, so we don't think life exists there. And the rings are frozen gas. Frozen hydrogen and helium is found in the atmosphere of Saturn. Uranus is even farther from the sun, and it's so far from the sun that we have liquid methane in the atmosphere. We're talking about temperatures that are very low, maybe 400 degrees, minus 400 degrees Fahrenheit, way too cold for life. Neptune, it gets even worse. Temperatures are so cold out there in the nether parts of the solar system that you have not only frozen methane but frozen ammonia, and so you're getting to the lowest possible temperatures. And we're going to talk about this later on when we get to another chapter. But the outer four planets, Jupiter, Saturn, Uranus, and Neptune, are called the Jovian planets. Jovian. And the Jovian planets all have something in common. They're farther from the sun, so they're colder, and they're larger, so they have very high. Each of them has very high gravity. Also, please don't forget that the asteroid belt is between Jupiter and Mars. So the asteroid belt separates the Jovian planets from the terrestrial planets. Now, these asteroids in the asteroid belt sometimes collide with one another, and chunks of rock enter Earth's atmosphere. When these chunks of asteroid enter the Earth's atmosphere, we call that a meteor. When a meteor strikes the surface of the Earth, we call it a meteorite. When chunks of rock way out here beyond Pluto come closer to Earth due to the gravitational pull of the sun and hit our planet, those are called comets. So comets come from way outside, on the very edges of our solar system, way out here. We'll talk about that more in later chapters. Next thing we want to talk about is the solar nebular theory. What's the solar nebular theory about? Well, the solar nebular theory is our best theory as to how our solar system, including the Earth and the Sun, formed. And here you can see three different pictures depicting the formation of our solar system. What must have happened first is something called a supernova. What that means is there was another star that existed before our sun about 5 billion years ago, and it exploded. And what happened next was that formed a cloud of gas and matter. Two forces acted upon this cloud of gas and matter. Those two forces would be the gravitational force and the centrifugal force. How do we know that? Because they act everywhere. It's the basic laws of physics. Matter attracts matter. So the gravitational pull of the Earth holds the moon in Earth's orbit. The gravitational pull of the sun holds the planets in the sun's orbit. The gravitational pull of the black hole in the center of our galaxy holds the stars within the Milky Way galaxy. So matter attracts matter. The centrifugal force is a different force. Best way to imagine the centrifugal force is this. Do any of you all like to watch the Winter Olympics? Imagine a skater and she's on the ice and she brings in her arms together. Does she start to spin around faster or slower? Faster. Okay, bear that in mind as we talk about this. So we've got this cloud of gas and matter. Would the gravity cause this cloud to expand or contract, do you think? Think about it for a moment. It'd have to contract, right? Because matter is going to be attracted to matter, not to the emptiness of outer space. So this sphere of gas and matter must have started to contract, just like that skater bringing her arms in closer on the ice. So that cloud started to spin because of the centrifugal force. And this sphere of gas and matter must have become a disk. That formed the ecliptic plane, with 99.9% of the matter concentrating in the center, forming the sun. Some matter, though, was far enough away from the center so that it started to orbit around the sun. And these eventually became the planets. Some chunks of matter, smaller even than planets, started to revolve around the planets and become moons. We know this is the best explanation for the formation of planet Earth 4.6 billion years ago, for the simple fact of the matter that we see other stars just like our sun, and they all form from the explosion of a larger star called a gaseous giant, and the gravity force and the centrifugal force forming planets and moons. What must have happened next can be understood by the next scientific theory, the homogeneous accretion theory. Homogeneous means the same. Accretion means to come together. The opposite of accretion is dispersion. So when the Earth came together, all the materials came together to form planet Earth, and that was a lot of kinetic energy, a lot of energy of motion, and that must have produced a lot of heat. So we know at the very beginning, 4.6 billion years ago, the Earth was a hot molten ball, liquid rock, very high temperatures. We're talking up to 2,000 degrees Celsius. Then, as this molten ball started to cool, some of the rock started to solidify. And being heavier than the surrounding molten rock, it collected into the center of the Earth, and it formed Earth's core. The Then other materials started to cool. So you had the inner core, and then you have the outer core, then the mantle, and then the crust. So the Earth started to differentiate, separate into these different layers. With the inner core at the center, later on we're going to learn that the inner core is made of solid iron, liquid outer core made of liquid iron, then the mantle made out of a rock called peridotite, and then the crust on the top. Oh, actually, we talk more about this in physical geology, but for now, let's move on. So Earth is a dynamic and evolving planet. Earth is an ever-changing planet. The positions of the continents have changed, and we're going to watch how North America grew and then also moved away from other continents and towards other continents. Our atmosphere formed from during the early Earth from a process called degassing, from volcanic eruptions releasing gases to form our atmosphere. The water on planet Earth may have had an extraterrestrial origin, because all of these chunks of rock are like those asteroids I mentioned before. Remember, they're mostly made of ice. They were in the early part of the solar system. There were collisions, many collisions between different asteroids containing ice, and they probably added the Earth's early water into our atmosphere. As the Earth started to cool down and become solid rock, that at the beginning you had some water, but it just evaporated because the Earth was so hot and went into the atmosphere, and it rained, and then over hundreds of millions of years the Earth cooled as it kept raining on the planet. Finally, there was solid rock on the surface of the Earth, and then we started to form an ocean and rivers and lakes. Here you can see a cross section of the Earth. You can see we've got the inner core, which is solid iron, the outer core, which is liquid iron, the mantle, which is made of a rock called peridotite, and then we have a crust on the very surface. Distance to the center of the Earth is 6,380 kilometers. However, this is what we all learned in high school, these layers of the Earth. However, we have to go a step further now and learn two new words. Okay, this is different from the lithosphere we talked about earlier. Unfortunately, it uses the same term, lithosphere, in terms of plate tectonics, and asthenosphere. Why in God's name do we have to learn these new terms? Well, the reason why is because the lithosphere contains the crust and the uppermost part of the mantle, and the asthenosphere underlies the lithosphere, and then you have the very bottom part of the mantle, which is called the lower mantle or the mesosphere. But let's just concentrate here on the lithosphere and the asthenosphere for a moment. The lithosphere, crust and uppermost part of the mantle, are the plates in plate tectonics. The plates consist of crust and the upper mantle, and they are rigid, and they move on top of the partially molten asthenosphere. Remember that for plate tectonics. The plates are lithospheric plates, which are rigid and move on top of the partially molten asthenosphere, such as the froth in a pot of convecting stew, like the stew you're making a beef stew. The froth is like the lithosphere moving on top of the asthenosphere. And the continents, since they're embedded in the lithosphere, they can move. There's two kinds of crust. Extra crispy and deep pan and hand tossed. I'm sorry, I'm getting hungry. There's two kinds of crust: oceanic crust and continental crust. Continental crust is the crust we have on the continents, and since we're on land, the rocks beneath you are the continental crust. But underneath the oceans, the crust is oceanic crust. And the rocks contained in the continental crust are less dense than the crust in the ocean. That's very important to remember for later on. The continental crust is less dense. So real quickly, density, you learned about that in high school, is equal to mass divided by unit volume. You can measure it in grams per cubic centimeter. What has a higher density? Gold or feathers? Gold, because a 1 inch by 1 inch by 1 inch cube of gold is heavier than a 1 inch by 1 inch cube of feathers, right? The oceanic lithosphere is made of denser rocks than the continental lithosphere. And keep that in the back of your mind for later on when we start talking about plate tectonics. So I mentioned the fact that the inner core is made of solid iron and the outer core is made of liquid iron. We know that from our earthquake data that you studied in physical geology if you took it. How do we know that the outer core is made of liquid iron? It's because of those earthquake waves. And I'm not going to go into that, but that's physical geology. But there's another reason, and it's Earth's magnetic field. The rotation of Earth's liquid outer core produces Earth's magnetic field. There must be a liquid outer core, or there would be no magnetic field around our planet. So, in summary, the inner core is made of what? Solid iron. The outer core is made of what? Liquid iron. And the mantle is made up of what? A rock called peridotite, which is made of a mineral called olivine. Let me show you what this rock looks like. If you take physical geology, we study this more, but for now I'll just show it to you. The mantle is made of a rock that looks like this. What color is it? If you're not colorblind, you can see that the rock is green in color from the green mineral olivine. That's what the mantle is made of. So we talked about there being two kinds of crusts, the continental crust and the oceanic crust. Another thing you also want to remember is besides the fact that the oceanic crust is denser than the continental crust, which we already mentioned, the oceanic crust is thinner than the continental crust. The oceanic crust is very thin, just a few kilometers thick, whereas the continental crust could be more than 100 kilometers thick. And I'm going to call it quits for today. I'm going to make another video for you tomorrow.